Welcome to the design, analysis, and operation of photovoltaic power systems with ETAP. For the next 45 minutes or so, we'll be talking about photovoltaic technology and how do we essentially utilize ETAP to enter information regarding photovoltaics, and essentially how do we migrate that model and move it into an online system. And then once we move it into an online system as well, how do we then go back to our simulation and kind of compare what we designed versus what we are now seeing in the actual system. So before we actually go through the entire process, just a quick recap on the solar technologies. There's many types out there, such as solar thermal, photovoltaic, which is semiconductor based, concentrated photovoltaic, that essentially utilizes light concentrating technology to pass the solar radiation onto a semiconductor. And there's other various technologies that are up and coming and under research, such as infrared solar cells, UV solar cells that you can put on your windows, 3D solar cells that give you more watts per square area, different types of materials besides semiconductors, exotic materials that can increase efficiency to almost 100%, and then PV thermal hybrid, where you can actually utilize the heat generated by the solar panels and use it for other applications. So for the next 45 minutes or so, we'll be focusing on photovoltaic only. And again, just as a recap regarding the photovoltaic electrical characteristics, typically when we look at the semiconductor, depending upon the manufacturer, there's obviously an internal equivalent circuit model that you can look at that has the diode resistances in series and parallel. But at the output of the photovoltaic panel, the manufacturers typically publish a PV curve and an IV curve. So the PV curve essentially is power versus voltage, and the IV curve is current versus voltage. So here we can see an example of an IV curve and how the curve varies as the cell temperature adjusts. So if your ambient temperature is increasing, that will actually have an impact on the overall cell temperature, and the performance essentially will drop on the PV panel. So it's important to cool them, especially if the ambient temperature is very high. There's also dependence on irradiance, which is basically the sunlight. That's typically in watt per meter square. So as we can see, from 200 to about 1,000, which is a theoretical maximum in the atmosphere. The current generated by the PV panels increases as you have more sunlight, so that's intuitive. When we look at the power curve and the IV curve and overlay them on top of each other, we can see a correlation between the two. At the peak of the power curve, it essentially corresponds to the knee point of the IV curve. So essentially on this point right here, that's where we essentially going to get maximum power. So all the inverter technologies try to make sure that they have a concept of maximum peak power tracking, or MPP control, where you can try to adjust the inverter such that the output is at the knee point, or essentially at the MPP point, under normal operating conditions during peak sunlight hours. So again, that's just the basic background, and this is a typical utility interconnection. So most of the PV panels are typically connected in an array of multiple PV modules. The block sizes vary depending upon the size of the entire solar farm. There could be 1 MVA blocks to 5 MVA blocks, each with their own collection system, with its own inverter, with a step-up transformer going into the main power collection station, and it's stepped up further into a grid environment. The connections are very similar, whether it's a solar farm versus commercial facilities, However, there are slight differences between the techniques and the reliability techniques used to connect them together, but the basic principle is the same. You have a PV array going through an inverter. There may or may not be a step-up transformer, and you're connecting into the grid. So that's the basic connection. As far as the modeling and analysis is concerned, we obviously want to design the PV system, size various equipment like cables, transformers, inverters, and perform various power system analysis like load flow, fault current, arc flash calculations, any disturbances that we want to introduce, such as a fault on the grid side, and look at the ride-through characteristics of the inverter, and the return on investment analysis, such as estimating the losses and the overall kilowatt hour or megawatt hour injection into the system. So there's different types of calculation modules utilized for each of these types of modeling and analysis. And within the ETAP solution, we'll be covering some of these technologies that have been introduced to help design and operate PV farms and PV systems in general. So in ETAP, you can have series and parallel connection of arrays. There's a comprehensive manufacturer model library that has IV and PV curve characteristics. We do adjust the performance of the PV and IV curve, as I mentioned earlier, based on various coefficients that are published by the vendors. There's even a solar irradiance calculator that will help us calculate the theoretical power for a brand new site. Various inverter modeling, including MPP, again, which is maximum peak power tracking mode. You can actually have grid side generator modeling, which means that the program doesn't really want you to have too much detail on the individual bits and pieces on the string cables and so on and so forth on the DC side, but you're essentially using ETAP to model a equivalent PV farm connected to the grid, and the focus is grid analysis. So ETAP does support that kind of connection, or you can go into a full detailed discrete DC model where you can build every single combiner box, junction box, every string cable, and do a complete detailed DC analysis from a solar farm or a solar system designer perspective. You can also do AC and DC analysis, and we'll look into that as well. The PV system is integrated with all of the ETAP analysis modules, so you can also use it for motor starting, transient stability, and other types of calculations, including protection. And it's also integrated with the ETAP real-time microgrid energy management system. So we'll take a quick glimpse at that as well. So the idea was to take one system in this presentation and walk it through design into commissioning, into operation, and basically the analysis at the end. So we decided to essentially create a system at our corporate facility. I'm just using that as an example in this PowerPoint. So we undertook an endeavor to essentially learn more about PV systems a few years back. So we essentially planned and did a lot of designing. We finally built this system, and as we were building, we had to go back and redesign our inverter strategies. We went back into the construction phase, commissioned and integrated the system, and now we're essentially managing this solar system as part of the corporate microgrid. So besides obviously understanding the way PV systems work, we also wanted to understand the issues faced by customers and typical issues faced during designing and constructing these types of systems. So I'll also talk a little bit about some of the lessons that we learned through the process. And obviously to conserve energy and lower the overall energy cost for our corporate building. So the objective for the overall system was to add panels and offset the daily peak, especially the summer peak. Our corporate office is based in Southern California. We are blessed to have clear blue skies, warm weather. So we should be able to take advantage of the summer peaks and offset the daily peak demand with the power from the PV panels, and overall reduce the overall energy consumption. And also we wanted to introduce electric vehicle chargers for EV vehicles to essentially get some of that solar energy in addition to energy we purchase from the utility, and do a composite. So we also added a weather station to measure the real-time data, so we can take a look at that as well. And then finally, we wanted to add a microgrid controller so we could see the performance of the system and adjust the strategies according to our energy saving objective. So this was the overall objective of the project. So I'll go through the planning and design phase of the project. The system was designed for about 180 kilowatts. We used the NREL multiplier to account for losses, any performance degradation of about 0.75. So we were expecting a peak kilowatt power of 133 kilowatts. So later on, I'll show you what we're actually getting versus what we estimated, but this was on paper in order to do a return on investment calculations. We expected savings due to the PV generation of about 220 megawatt hour for the whole year. And the annual savings in electricity used to be approximately 50%. Now, not going through all the numbers in details, but as you can see in any commercial facility, whether it's a data center or a commercial office building, whatever it may be, the biggest factor is, or the biggest energy consumer is cooling, and any cooling fans or HVAC units. And then the lighting, computer servers, which are receptacles, and any other process-related items. They're up there in kilowatt usage, but the biggest consumer of power, obviously, is the HVAC units. So that was the main goal, to cut down the demand, especially during peak afternoon, because that's when the HVAC units are running at their maximum power, and that's really the peak that we wanted to shave using the PV panels. So we started with that, and we went into the economic justification. This is just a quick summary of the output of the economic justification. And as you can see, the calculation was done for a whole year, and we were expecting savings of about $27,000 on our electricity bill for each year. So if you multiply that times 10, it would essentially give you about $250,000 or $300,000 of savings over 10 years, which was essentially the cost of the solar panels alone. That wasn't really the total cost of the project, but essentially was offsetting the direct cost of the solar panels. And there were about 564 solar panels, which I'll show you later on. So we obviously had to go into the architectural phase, and that's typical of any PV system project as well, and design the from an architectural point of view, how the panels will fit, what are the easements and the structure layout. I'm not showing every single architectural drawing, but this is the overall plan view, showing that we essentially have the ETAP corporate office building. We have our parking lot, and essentially there's a solar car shade covering 2 rows of parking, and then one all the way in the back. So the 3 of them put together is about 564 individual PV modules that were essentially going to be placed. All right, so after the initial architectural drawing, another typical thing that's done is an artist rendering. So this is what the artist rendering looks like. For those of you who may not have seen the ETAP office, have not had the opportunity to come visit us, you can see that's really our corporate office, and this is the artist rendering of the solar carport. And the outcome is very similar to what you see here, and I have some pictures later on for you to see. So again, the panel was supposed to do daily peak shaving. In here, the peak shaving is indicated by the load, which is in red. The resource is essentially in yellow. So what we expect to see is this blue line, which is between about 10 to 4 p.m. We lower our peak demand. And then obviously PV chargers, I've already mentioned, we added 2 of them into the system. We did not use a sophisticated way like this to determine our weather. This is what would be used in Hawaii. If the coconut is wet, it's raining. We did something a little bit more sophisticated. We added a weather station that has communication back to our SCADA server that measures different variables such as wind speed, humidity, irradiance, and so on. And you'll get a look at that in a little bit. We added electronic control onto the thermostat so we can regulate our demand as well. And then we went to the actual electrical schematic. And this is just an overview of the electrical schematic, and I'll just highlight some of the main points here. These are essentially the PV strings. This doesn't represent individual PV module, but a string that's going into a junction box and into a combiner box. And each of these combiners, you have about 9 to 10 strings each, but they're variable. You can see 2 10s, 9s, 11s, and 7s. And this was essentially done because of the layout of the physical space, not for any other intentional purpose. Ideally, you would like this to be balanced as far as possible, but we can see that we have a little bit more room to grow here in combiner box number 7 if you want to expand further into the remaining car spaces. The combiners essentially end up going into the inverter, which is shown here with this rectangle. So we opted for a 250 kVA inverter, grid-tied inverter, and that goes essentially back into the main switchboard that's fed by the local utility here, which is Southern California Edison, and that's a step-down transformer, which is the main service entrance T1, and that's a 750 kVA service, 11 kV down to 480 volt service. So that's basically the overall setup of the system, and we'll see the same thing on the ETAP side. So we went through the construction phase. I'll just skip through these slides very quickly so you can get a flavor of the kind of effort that went into constructing the system. Here's a finished product, almost finished product of the PV panels, and these are essentially 305 watt polycrystalline modules that were plugged in. The communications were essentially set up as well for each of the incomers from the utility, from the inverter itself. And then we also installed branch circuit monitoring for some of the loads that we wanted to measure in a little bit more detail, especially the HVAC units. We also put metering onto the UPS, which serves the data center that we run within the facility, as well as the critical computers, especially for the developers that are working very hard on the ETAP software. We went through the commissioning phase, as you can see here. We're just going through a test right now. And we actually had our first injection into the meter, so we can actually see negative power going into the Southern California Edison meter. So we were actually selling the moment we energized the system. Now, when we talk about energization and working on equipment, one of the things we always talk about is arc flash. We were on a time scale to get the work done, so some of the work was done energized, but typically you would do this with hot gloves and appropriate PPE. In this case, you can see these two gentlemen actually adding a new circuit breaker onto a live bus, but using hot gloves and wearing appropriate protection. And then we finally went through and connected everything together. So the solar inverter, the combiners, the weather station, the UPS, the thermostats, and the data center are all communicating into one single location that's being monitored by ETAP real-time, and it's being broadcasted into a web dashboard that we'll take a look at in a little bit. And that's a first version of that dashboard that you can see on the web or a tablet. So let me first talk about the lessons learned before we jump into the ETAP side. These are lessons learned during the construction phase. So what we did learn was when we are purchasing combiner boxes, there's typically an option to either have a fuse disconnect or just a disconnect. And we landed up with an option to have a simple disconnect, and that disconnect is from the PV panels to the combiner box. And you can see that disconnect is shown here in the rectangle and the fuse is right here. What we were not told from the vendor that the fuse disconnect was optional. So obviously we went ahead and purchased what was standard, and we later on found out from during the commissioning phase that we should have had a fused disconnect. So it had to be retrofitted into the system. As you can see here, the fuses were retrofit in, but that it's essentially caused additional work. So you should pay attention to your local codes to make sure that from the DC side into the combiner, whether a fused disconnect is required or not. And this fuse is there to protect the cable going to the inverter itself. The inverters themselves have to be fused on the DC input side, which is also an optional extra. And again, you have to make sure that when you're ordering the inverters, check with the local codes to make sure whether this fuse on the DC input side is required or not. And that fuse is shown here in this orange color. So these two fuses are there to make sure the fault on this cable is cleared and the cable is protected from a fault on either side of the equipment or an internal fault. The other thing that we learned very early on was to factor spares into the design. In the previous pictures, you may or may not have noticed, we actually had to do some trenching to lay out cables. Good practice to always make sure that there are sufficient spares or conduits essentially provided to accommodate for illumination, any plug-in electric vehicles, security cameras, plus the communication and control power, because the combiners themselves may not be self-powered. They will require control power, 12 volt or 24 volt DC input, and that has to be provided from the facility to the combiner box itself. It cannot be provided from the PV panel because at night you will lose communication altogether. So it has to be sustained power. One of the things that does create a problem, and it has to be done in parallel, is illumination. Again, you have to do a lumen test and make sure that whenever there's any PV system going in, what are the illumination requirements around that facility to make sure that, again, the appropriate illumination type is used. In our case, we used LED lighting to reduce the amount of power. And then appropriate cables are run to make sure there's sufficient lumens available throughout the facility. Again, that has to be determined by the local inspection that's done at the facility. So here's a quick overview of the yearly production. This is 1 year's worth of data that we've collected from 2015, from last year, February 2015 to February 2016. So it's very current. And as you can see that the output from the system appears to be cyclical. So you can see in February we were somewhere about 65 kilowatts of production, and we cycled down to about 45 or so, and then we're actually coming back up, and this is February right here, and we're coming back to our 65 kilowatt levels. If I trend the line between the two, I should not see any degradation in performance because of aging, because this is only 1 year's worth of data, and the system has been in place for the last 2 years. But over time, you will see that from month to month, it may not return back to the exact same levels, and that's just degradation of the material itself. The other factor, in case it does not return back to the same level, could be just simple dirt on the panels, and typical practice is to clean them every 3 to 6 months, 6 months preferably, complete cleaning to make sure they're operating at optimal efficiency. Now, if you remember in the initial estimates, we sized the system at 180 kilowatts. We applied an NREL factor of 0.75, as I had mentioned, and we expected the output to be about 133 kilowatts peak summer. So we did not really achieve 133 kilowatts, but we did achieve about 125 or so. So we were not that far away from the NREL factor that kind of estimated it. And this is actual production data showing us. The same data is actually folded together. So this is again almost 1 year's worth of data folded together from 6 a.m. all the way to midnight. And as you can see, most of the production starts around 9 a.m. and it essentially ends anywhere between 6 to 8:30 p.m. And this large shift is also because of daylight savings and the fact that we are in the northern latitude, so we do have later sun in summer. We do see a shift. Plus, we have an hour time change that causes the production time to kind of shift around. So that has to be factored in when we are doing the yearly analysis. So instead of looking at this data in this fashion, I took a single day, and this is what we're going to analyze inside ETAP right now. So I took consumption versus PV generation data, which is for February 15th. So it's about two days ago. And this blue line that we're seeing is the load. The red line is the PV generation. And this is essentially my 24-hour clock in a circular fashion. So again, the same type of behavior can be seen. The PV generation is happening mostly, it starts around 9 to 10 a.m. and it's maxing out around 1 to 2 p.m. and it starts dropping off till it gets to about 5 or 6 p.m. And we are essentially in the winter to early spring months, so we do see the sun come up a little bit early and then set around 5:30 p.m. So that's why you will see the output dropping that fast, at least in this location. So if I take a slice, and that slice is, let's say, 1 p.m. So 1 p.m. we can see that the PV generation is 65 kilowatts. The load is almost about 100 kilowatts or so. So I'm going to switch over to ETAP and show you the model here. We have two different types of models, and we're going to run that analysis in this model and see what we get. So first of all, I have the entire system zoomed out so you can see the overall structure. The lines that you see in blue are DC. The lines in black are AC. And there's two different systems here. I have one system up here, which is a detailed model of the PV system, having every single string cable and the combiner box to the inverter into the main switchboard. And there's another system down here, which is taking the entire DC system, making it equivalent into a single source, and I have the entire AC network. So if I was doing grid interconnection studies, I would be using a single source generation, single PV source generation, and then modeling the details of the grid on the right-hand side. And my main focus would be to see what happens in the grid when I have PV in my system. I'm more interested in the reliability and security of the grid. I don't need to see the details of the PV system, so I can make all of these panels equivalent, have an inverter, and inject the power into my AC bus. And that component, which is a PV array equivalent, AC PV array equivalent component, is available on the ETAP toolbar right here. So if I open it up, we can see that I have my PV panel selected. I actually grabbed it from the library. So this is ReneSola 305 watt panel, polycrystalline, and this is the PV and IV curve as I was describing earlier. So this is actually coming from the library. These are the performance coefficients that were provided by the vendor, so I'm essentially utilizing those. And then I have about 12 panels in series, so that basically makes one single string of the PV system that we have. And that one string actually combines together in these panels to create essentially 440 volt DC. So it's like putting 12 AAA batteries together and making a larger voltage battery, so that we're essentially putting 12 of these in series and 47 of them in parallel to give us a total kilowatt DC of about 172 and a total DC voltage of about 440, as I mentioned earlier, about 564 panels and about 400 amps DC that we expect from all these panels going into the inverter. And then I can describe the inverter characteristics itself. As I mentioned earlier, it's a 250 kVA inverter at 480 volt AC side, and we plugged in the efficiency at different percent loading. Now for inverters, the efficiency curve is not very dramatic. It is quite different for induction machines or any other type of load, but because PV array is mostly electronics based, the output for larger inverters or the efficiency of a larger inverter is not that dramatically different as the load increases or decreases in the system, but nonetheless it has to be entered in appropriately if you want accurate simulation of losses from the system. So if we look at the same PV array, which is an equivalent, I have 564 panels here with an inverter injecting power into the network. If I step back to my diagram here, this is exactly the same system. If I open up one of these panels, you will see it's the same panel here, 12 of them, but only one in parallel because I'm representing PVA1 as one string. And that's my choice in this particular system. There's no inverter option here because this is a DC element, and this element you can find from the PV array toolbar here, the DC toolbar, and you can drag and drop that into your model. But from the PV array, I have my string cable, which has its own individual fuse going to the combiner cable, and this bus essentially represents the combiner point inside the inverter. So actually, technically, this DC bus is part of the inverter, and this bus right here is the combiner. And these are the individual fuses that we retrofit later on inside the combiner box to create a fused disconnect. So you'll see about 47 of those here. So the entire system you see on the top is discretely modeled DC with the combiner, string cables with the inverter to the AC side, and then the network you see on the bottom is all of the blue stuff combined into one equivalent piece back into the grid. So when we actually go ahead and run calculations within ETAP, typically when we run simulations, in this case, I'm actually producing about 150 kilowatt. My load is about 157.9. I'm actually buying about 7.5. This is one of the scenarios that we had created early on in the design phase. But coming back to the simulation that we were looking at on the slide, this 1 p.m. one, where the load was 99.19 and the PV generation was 65. Let's see what happens here. So if I go ahead and change the load to 99.19, I'm just changing it manually on the rating side. You can also change it using the loading categories here. I'm just simplifying things. And we will go ahead and put the PV generation as well over here. So the PV generation that was measured was about 642. And when I say PV generation, I mean the irradiance on the PV panel, not the actual kilowatt output itself. Theoretical was 875. So let me explain what these two values mean. So back to ETAP. Now, based on the location, 33.6 north and 117 west, if I look at February 15th at 1 p.m. and go ahead and calculate, you'll see that the theoretical irradiance should have been about 875. So this is the irradiance that would have been falling on the panels, provided I had clear skies, no smog, no fog, no atmospheric issues whatsoever. The sunlight comes in perfectly diffused into the atmosphere and falls on the panel. So this is what we call the theoretical value. And if I update, I press on that update button right here, what you will see is that 875 gets plugged into one of my generation categories. There's another factor here that you have to plug in, which is the ambient temperature, because again, if you remember from those characteristic curves, the ambient temperature will affect the IV characteristics, and it'll affect the overall output of the panel. The difference is not a whole lot, but it's sufficient that it should be factored in. If the ambient was 30 degrees, you can see that the output drops about 4 kilowatts or so. But in a much larger system, that 4 kilowatts can add up into significant difference in the output. So let's assume the ambient was 30 because this is about 1 p.m. and this week actually has been a warm week, record-breaking temperatures in Southern California. So I'm going to go ahead and run that calculation real quick. And we see that the output, based on ideal conditions, should have been 140 kilowatt. But obviously we did not have ideal conditions. Based on my weather station that I mentioned earlier, instead of getting 875 watt per meter square, I actually got 642 on that day. And that was from the archive data. So in reality, if I was to simulate this correctly, this would be 642 watt per meter square. And that simulation would have shown that I should have been producing 100 kilowatts or so, and selling about 8 kilowatts. So my net meter would have shown negative 8 kilowatt going into the utility. However, when we look at that and compare it with the PV generation values, so simulated value based on theoretical irradiance we saw was 140. Simulated value based on actual irradiance, which is 642, was about 100, which we just saw. But measured was 65. If I go back to my chart, you can see at 1 p.m. Measured was actually 65. So we can see that there's an approximately 65 to 75% difference between what we are simulating versus what's actually happening in the system. Now, why is there a difference? Now, it kind of matches up with that NREL factor that I was mentioning earlier, 0.75. But why does that happen? So some of the factors in this particular network or in this particular system are as follows. We are utilizing averages. So I'm looking at an hourly average value to do this comparison. I'm not using exact instantaneous value. So if I want to be more accurate and get a better feel for this deviation, I should look at an actual instantaneous value instead of looking at averages for a whole hour, because I could have multiple measurements and come up with an average that doesn't really correlate very well between the irradiance and the actual generation. Then we actually have shading differences. So depending upon the location of the structure with respect to surrounding buildings, shading is a factor. Now, in commercial spaces, that may or may not be controllable, but obviously if you're dealing with a solar farm, that is easily managed by just adjusting the spacing between the panels so that the shadow of one does not affect the other. There's also another factor, which is surface dirt, and other variables such as losses and things of that nature. But overall, we have over different time slices for that day, we have anywhere from 65 to 75% deviation from real time measured versus simulated. And we kind of expected that, again, using that NREL factor. So what we intend to do is come up with factors for each of these items, the averages, the shading, the surface dirt, and we're going to essentially adjust our model so that we can get a little bit more accurate prediction, a little bit accurate what if, without really using forecasted irradiance. So if I wanted to know what's going to happen tomorrow and adjust my generation accordingly, I can use this model and really not rely on weather data necessarily. And then we're going to do further analysis and hopefully in another webinar to follow and compare the forecasted irradiance from a weather service versus this forecast model that we're going to come up with. So again, this was just a single day analysis to give you an idea what ends up happening between theoretical versus actually measured values. They may or may not match, but there are various reasons associated with it. Now, some of the other lessons that we learned, especially with shading, is to avoid strings with panels at different tilt angles. Now you can take a look at this structure and you can see the problem right away. The irradiance is not evenly distributed along the panels. Though from this picture the curve may not look that much, but there is sufficient tilt in these panels that are different from each other. So each string is tilted in a different manner. If you recall, when I put in an actual irradiance of 642 watt per meter square, again, we're assuming that all the panels are facing the sun appropriately, or they're being tracked in such a manner that the tilt angles are optimal. But as we can see here, the tilt angles are not optimal, and that really accounts for that difference in the model versus the real-time measured value. So the string should be organized, again, such that panels of similar orientation are strung together. So you can actually have strings going this way so that they're all at the same tilt angle, instead of having strings going around or across the solar panels. Now, in our case, the strings are actually going across, and that was done purely for construction purpose. The tilts are more for aesthetic purpose. There was no other scientific reason for doing it in this manner. It was mostly for aesthetic purposes. So this was a significant factor if the panels are not at the same tilt angle. So let me go back to ETAP here real quick. and go back into my DC side and show you the same calculation here. Slightly different numbers, but if I go ahead and run a DC power flow, you will see that we obviously calculate the power injection from each of these panels. You can see that each of them is producing 3.5 kilowatt, which will really not happen because they're not at the same tilt angles. But because the number of strings are different, you'll see 21, 17, 21, and so on. So you can see the voltages at each combiner. You can see the flow through each of the combiners, the input into the inverter. And then we kind of stop right here because this is the extent of the DC power flow. You can save this operating value into the inverter and then follow up with the AC calculation. So you can now see the AC injection into the grid. This is one way of doing it, but what we've done is we've actually introduced another type of calculation inside ETAP, which allows us to do a complete AC and DC simulation in one shot. So you can see my DC power and my AC power injection into the grid in one single calculation without actually having to go back and forth and iteratively trying to solve the AC side and the DC side. Obviously, if you're not interested in the details of what's happening on the DC network, you don't really need to model it in this fidelity. You can just look at an AC only equivalent circuit. Okay, so some of the other lessons learned, to summarize them real quick. So the other thing that we learned was grounding. Now, this is a little bit more with respect to National Electric Code. That's a little bit more US based, but I'm sure there's similar electric codes in other countries such as the Canadian, UK. They all have their local codes. So for grounding, definitely you have to follow the local code of the region you're in. In US, North America, California, we're following NEC. So NEC requires that all PV systems over 50 volts have at least one current carrying conductor connected to ground. So that's from 690.41. And all exposed metal parts, conduits, enclosures, everything associated with the PV system, regardless of voltage, should also be grounded. That's 690.43. And that's just to make sure that if in case there's a ground fault because of an accidental short in ground, one or more in one or more current carrying conductors, you can actually have a DC arc depending upon the voltage level and the amount of current being carried. And if the fault is not properly cleared, the arc can cause a fire hazard. So there's another calculation that we've added within ETAP, and unfortunately we don't have time to go through all the details, which is DC arc flash. So this will essentially allow you to place a fault at certain points in the system. So you can either right click and fault or go into the study case and fault. Select the short circuit model for various sources such as batteries, rectifiers, motors, inverters, and so on. Select from different arc flash methodologies, and ETAP's actually the only program right now that supports 3 different methods based on the complexity of the system for doing arc flash calculations such as maximum power, Stokes and Oppenlander. And you can actually use the DC arc flash with the protected devices as well, just like the AC arc flash module, to calculate what is the arcing current, the fault clearing time, instant energy, and so on and so forth. Now, in my system, I've not set up all my protected devices appropriately, so we will essentially not get an output, but we do see what the fault current levels are over here. So there is a DC arc flash calculation program or module available inside ETAP to help you make sure that the grounding is done appropriately and it is safe, especially if you're planning to use planning to do work on the system energized. It will help you understand what is the appropriate PPE to be used. Obviously, in PV systems, the best thing to do is operate on the system at night, so there's hardly any irradiance, there's hardly any generation from the panels, and most of the work can be done safely at night. But in cases if it has to be done during the day, because of some kind of fault in the system, it's not possible to shut down the entire system. You may want to run this calculation and determine the appropriate PPE and label the equipment accordingly. On the array grounding, the equipment grounding conductor, which is EGC, and the grounding electrode conductor, GEC, should also be installed appropriately. 690.47C tells us that. And then what we landed up doing in our system was we put a solid bare copper number 8 size wire, and that's AWG, American wire gauge size, to essentially have a common ground, common EGC and grounding electrode conductor to have a appropriate system ground and the equipment ground going finally into the main ground of the building. So the PV structure was also grounded to the main ground, or the UFER ground, as we call it, named after the inventor of this type of grounding. It's essentially a ground conductor encased in concrete. So there is a UFER ground available for most commercial structures here in North America. PV structure was actually grounded to it, according to Article 250.52. So again, this is just a quick overview of the grounding scheme that we used in this building. This is the PV string from our solar car park, and we took the bond from the aluminum frame of the PV panel to a grounding bus bar within the combiner box. That itself was connected to the structure ground and grounded, and the equipment ground was carried through and brought into the ground of the inverter, which also is grounded back to the actual switchboard. Voltage is incorrect, it's actually 480 volt, and everything is bonded together through a common UFER ground. So that's essentially things that we learned on the grounding side. This was through, again, through the commissioning phase. We had initially just grounded the system directly to the UFER ground, and we had not carried the ground wire over to the main system ground. So we essentially had to go back and add this EGC wire back in to make sure that these two systems were tied together and going to a common ground. So let's really talk a little bit about the savings before we go into the real-time side of things. So we installed the system back in 2013. We've been operating it since then. I just picked a sample month, which is August, because it happens to be a peak month as far as power consumption is concerned in Southern California, at least for our building. So as you can see in 2012, which is in blue, this is before the PV system was plugged in. The kilowatt hours used was about 41,000. Number of days is basically the billing cycle from the local utility. But the other key component here is the maximum demand. It used to be about 144 kilowatts, and this is the actual bill, about $7,800 or $8,000 for the month of August. And this is essentially the TOU rate, or time of use rate. And that varies from utility to utility. This is the schedule that's provided by Southern California Edison, which is GS2, General Schedule number 2, used for commercial facilities. And that's the schedule that we were on. And then August 2013, we plugged the system in, which is shown in green. So that's essentially when we switched over to green energy. And you can see that the kilowatt hour usage dropped significantly down to 27,000 kilowatt hours. And we are essentially on net metering. Hence, you will see that this offset or this drop is because we were producing the difference, or almost the difference of the two, and providing the power to SCE during peak summer months. The kilowatt demand, we managed to drop it down from 144 to 115. So that was accomplished through the microgrid controller, or essentially ETAP real time. We are managing this maximum demand so that it's comfortable temperature, but we do not reach a maximum demand of 144, because there's in the GS2 schedule, and again it varies from utility to utility, you will find that there's a time of use charge on the kilowatt hour, and you'll find that there's a demand charge on the peak demand. So these two are the main charges that add up together that make up this $7,800. Obviously there's other pieces or components to the bill, but these two are the main contributors. So if you can lower both of them, you can lower the bottom line or the overall bill that you receive. So 2013, we saw a drop down to 6,300. 2014, we tweaked and optimized a little bit more, and we went down to about 5,900. And then this past year, even though our consumption went up, our demand went up, but you can see that our bill was still lower. And this was done by us negotiating with the local utility, and that's something, again, is part of the lessons learned, to make sure that you're on the correct schedule. We switched our time of use rate. We switched over from GS2 to GS2R, which is a general schedule rate for renewables, which was offered again in 2015. So that essentially lowered the time of use and demand charge. So again, reduce the overall bill. So if we add up the savings put together, we're not exactly in line with what we had estimated in our original estimate, but we are close. And hopefully in the next webinar we can go through a yearly analysis of the cost as well, and the ROI of putting such systems with the current utility rate schedules that are being offered. Here's a quick event that I just wanted to share with you, which is maintenance shutdown event. So these are essentially, we're tracking instantaneous values, and this is back from 2013, and we can see what we're tracking is actually the demand in the system. The negative values are correct. That's essentially where we were actually injecting power back into the network. But as we can see over here, at this particular date on August 19th, we were somewhere in the range of 102 to 110 kilowatts. Everything was fine. We were generating power, and we had an outage on the inverter. So as soon as we had an outage, we hit the maximum demand for that month, and obviously we were billed the maximum demand charge for that month. But you can see overall for the month we were doing very well till that outage event happened. So this is again just another example that you have to make sure that any maintenance or any outages are prevented during peak operating time, because once you have an outage, you will hit the kilowatt demand and the corresponding charge, and that applies for the whole month, and it kind of negates the benefit of having the PV array system. So this again justifies the need to actually have a controller in the system that can quickly correct for this situation and not allow the peak demand to continue to a higher level, because there could be additional load coming on at this time that could have taken this peak demand further into the 130, 140 kilowatt range. So in conclusion from the design side, we can actually have considerable cost savings by reducing the kilowatt demand. As I mentioned earlier, you shut down the inverter for maintenance during off-peak hours, and installation of any peak demand reduction system like ETAP real-time will essentially give you direct return on investment, because you will see a reduction in the peak demand charge. So with that, let me quickly show you what we're seeing on the real-time side, and let's take an example of right now, and let's see what we get from our simulation. So what we're seeing right now is an actual view into what's happening in the PV system. We're actually producing about 43 kilowatts or so, and the power that we're buying from the utility is about 20 kilowatts. Our load is about 65. And you can actually see right here, around the time, somewhere in the middle when the webinar began, the load essentially went up while we were going through our other discussions. And that's essentially the air conditioning that's coming on because we're approaching 10 to 11 a.m. The outside temperature is past the set point of the thermostat, so that's actually triggering certain air conditioning within the building. Now, that same single line diagram that I showed you on the ETAP side with these strings has been replicated, actually exported and replicated here onto this dashboard. So it's essentially a live view, or the main actual single line diagram. As you can see, those individual strings with the amps connected to the combiner box, they're shown here. So you can quickly build the design model inside ETAP, export that model, and have it available as part of the dashboard for operating the system. So you can see from each section, from each combiner, we are seeing about 9 to 10 kilowatts. And obviously the last string, as I'd mentioned, was only the last group was only 7 strings. So you'll see about 7 kilowatts or so coming from that group. Going into the inverter, here's the inverter output, and here's the power that we're buying from the utility. And we can see what's going on with the individual breakers within the system. And as you can see, the bulk of the load is air conditioning and the computers in the system. So that makes up the maximum load that we're seeing at this point in time. I can actually drill down further, and you can see more detail about what's going on within the data center down to the PDU level. You can actually then also drill down into the air conditioning side, and you can see what's going on with each and every single air conditioner in the system. And we can see that there's actually 2 of them running right now, accounting where we're essentially definitely want to keep them cool, and the cafeteria where people are actually probably enjoying breakfast. So that kind of makes sense. That's where the air conditioning is actually running right now. If I look further into other types of dashboards here, I can see here's what's going on with my PV array itself. I'm seeing about 612 watt per meter square of irradiance in my system. The temperature is about 76 Fahrenheit, and the colors actually are telling me here's what's going on the panel. The lighter the color, the more power is being produced. The darker the color that's approaching darkness, the less power the panel is going to produce. So these panels are actually color coded too, to tell you if there is any panel producing less power because of a cloud that comes by, or the sun angle is changed. So you will see a different gradient as you approach extremes of the day or extreme weather conditions in the system. Here's a little bit more weather data that we're collecting from ETAP real-time, and that can actually be displayed in the ETAP model as well, not just this dashboard. So if I take 613 watt per meter square and apply it to my model, and that ambient temperature probably corresponds to about 22 degrees Celsius. And if I run my power flow calculation, I should have been seeing about 98 kilowatts from these panels. I should also change my load correspondingly. The load was actually about 64 kilowatts or so in the system. So I should have been selling about 34, but that's really not what's happening in my system. What I'm actually doing is buying 15. So there's definite difference between the design model and the planning model. And by actually having them in ETAP itself, you can actually now start tuning the model to make sure that what you get from your simulation and what you're seeing from the real system actually corresponds and jives together. And ETAP does have tools that allow you to do that. And we're actually going to do that in this model, and hopefully have that available for you to see in the next webinar. Have that tuned as well as using forecasted weather values. Other things we can do in this dashboard include the HVAC monitoring, so you can see what's going on with temperature in different parts of the building. As you can see, accounting is set to 71, and we know that because the air conditioning is running, so it's measuring about 71 Fahrenheit here. And there's air conditioning running in the cafeteria too, so that's sitting at about 65 Fahrenheit. So that kind of confirms what we're seeing with the electrical side as well. There's a section for alarms, so if there are any alarms defined, they would show up here. Right now the system appears to be running perfectly. And there's also a trending application, and this is how I obtained the data that I showed you earlier. So I can actually go into my real power for my inverter, my main incomer, and the consumption. So I'm actually trending real data right now that I'm measuring from the system. You can actually combine this together and see it in one chart. And this is what we're seeing as live data. Or you can go to a user-defined date. And if I go back to the 15th, 12 a.m. to the 15th, let's say 11 p.m., here's essentially how I got my data. So you can see very quickly in how fast I was able to pull up this information and see what went on that day. But you also have the capability to go further back. I'm going now 15 days or so back into the system, and we can quickly see what happened here. And every day you can see there's a little bit of extra generation, excess generation, which is the yellow line that goes over the red line, and that's really where we're actually selling power back into the grid. These two dates, you will see that there's more power being sold because this happens to be weekend, Saturday, Sunday, and that repeats again, Saturday and Sunday. So that kind of, again, jives with what actually happens within the system. Other things you can do here is energy accounting, and that's how I actually got my kilowatt hour numbers. You can also see the communication diagram to make sure everything's operating correctly, and we're using various protocols here like Modbus, 61850, and SNMP, and amongst others. And here's the neat part. I can also do my simulation from right here. So here's how my system is running right now. And what if I just wanted a quick control decision to be made? Well, what if I shut down all the air conditioners in the building right now? So I can double click on those two breakers. You'll notice that I originally had them in black, and I'm going to go ahead and open them so it'll turn it to green. So I'm opening these two breakers, and I'm going to press run. Now I'm actually running a simulation inside ETAP and bringing those results back into my dashboard. And you can do this from anywhere, from within your network or outside your network, depending upon your security levels. And you can see that if you were to shut down those two air conditioners, yep, you would be actually selling about 1.5 kilowatts or so back into the grid. And as you cut more and more load into the system, we obviously expect more power to flow back into the grid. So this type of simulation allows you to even quickly come up with what-if scenarios, and these are essentially decision strategies you can make for a more complex system. I'm using a simple system to help illustrate the capabilities of the program, but it doesn't necessarily have to be a renewable system. It could be any industrial, commercial, or utility distribution system, and you can do the same type of what-if analysis straight on the dashboard. So hopefully I've managed to convey from design all the way into operations in a short time frame. There's obviously a lot more details involved in the modeling side of things, and depending upon your response and requirements, we can actually organize additional webinars and perhaps go into more specific details on each of these items. Once again, I appreciate your time and apologize if it took longer than expected. And thank you again for attending this webinar.